Welcome back to The Explainer. Today, we're diving into something that feels, honestly, almost like modern magic. We're going to talk about building a custom computer processor entirely from scratch using Verilog HDL. We are figuring out how to take a raw, physical piece of hardware and give it a completely custom digital brain. So, ever actually wanted to build a computer brain? It sounds totally sci-fi, right? Or at least something reserved for massive tech conglomerates with multi-billion-dollar fabrication plants. But you see, that's the absolute magic of the FPGA, or Field Programmable Gate Array. Think of an FPGA as this brilliant, blank digital canvas. Instead of soldering physical wires, we're literally going to write the very DNA of a functional processor in code, and then just watch the hardware configure itself to become that exact machine. To pull this off, we're zeroing in on a very specific architectural path, a single-cycle RISC processor. Now, RISC stands for Reduced Instruction Set Computer. The core challenge we're tackling here is creating a processor that executes a relatively small, highly efficient set of fixed-length instructions. And the solution is right there in the name, single cycle. It's a beautiful design that ensures every single instruction, from fetching it to decoding it, all the way to executing it, completes in exactly one single tick of the clock. All right, here's our roadmap for today. 1. The single cycle challenge. 2. The RISC architecture blueprint. 3. Designing the data path. 4. Building with Verilog HDL. And 5. Performance and final results. Let's jump right in.
Section 1. The Single Cycle Challenge.
Think about the modern superscalar processors, like the ones sitting in your smartphone or laptop right now. They're incredibly fast, sure, but logistically, they are nightmares. They require intense hazard handling, complex pipeline management, and crazy speculation mechanisms, mostly because they're juggling so many instructions at different stages of execution all at once. We're contrasting that with the elegant simplicity of a single-cycle approach. Here, everything happens cleanly and predictably. One instruction goes in, one instruction finishes before the next one even thinks about beginning. It just vastly simplifies the control logic. Moving on to Section 2, the RISC architecture blueprint. This language is our custom 32-bit instruction set architecture, or ISA. To make hardware decoding as efficient as possible, our instructions follow a really strict, fixed 32-bit format. We actually break them down into 3 core types. First up is R-type, which handles operations strictly between the processor's internal registers. Second, we have I-type, managing immediate values and accessing external memory. And finally, J-type, which handles unconditional jumps, basically allowing our code to leap around during execution. So the real question is, what specific words are in this vocabulary? Well, our custom instruction set includes basic but seriously powerful commands. We've got our arithmetic, like add and subtract. We have our logical gates, your AND, OR, and XOR. Then there are memory commands, like load word and store word. Plus branching commands, like branch on equal and jump. It's a lean, mean vocabulary that is just perfectly optimized for a single-cycle hardware setup. Section 3. Designing the data path. Now we're looking at the anatomy of our processor, the interconnected core modules of the data path itself. We've got the program counter keeping our exact place in the code. We have the instruction memory holding the program. There's a register file featuring 32 general-purpose 32-bit registers for lightning-fast temporary storage. We have the Arithmetic Logic Unit, the data memory for longer-term storage, and, of course, the control unit. That control unit acts like a traffic cop, taking the instruction and telling every other piece exactly what it needs to do. I really want to zoom in on the ALU, the Arithmetic Logic Unit, for a second. Think of the ALU as the mathematical beating heart of the processor. It doesn't just perform all those arithmetic and logical operations we talked about, like addition and XOR. It also outputs a supercritical 0 flag. This flag is actually what allows the processor to make decisions. Say we're comparing 2 values to see if they're equal, the ALU subtracts them. If the result is 0, boom, the flag goes up, and the control unit knows it's time to branch to a new piece of code. All right, Section 4, Building with Verilog HDL. There's a quote from the source material that absolutely hits the nail on the head regarding why we even use FPGAs in Verilog. Historically, if you wanted to verify a processor design, you had to send it off to a fabrication plant, spend millions of dollars, and then wait months for custom silicon chips to come back. But now, FPGA-based design lets engineers and students describe the hardware and code and test that architecture directly on physical hardware instantly. It's an absolute game changer for learning and development. Let's walk chronologically through how we actually pull this off. Step 1, we write modular Verilog code. We're coding the ALU, the register file, and the program counter as completely separate testable blocks. Step 2, we run simulations via Vivado test benches to verify that the data flows perfectly in a virtual environment. Step 3, once that simulation is totally flawless, we synthesize the design. That translates our code into a physical layout for the RTX 7 FPGA board. And finally, step 4, definitely the most exciting part, we deploy it and verify the real-time execution right there on the chip. Which brings us to Section 5, Performance and Final Results. Let's talk about the final physical footprint of our custom processor on that RTX 7 board. The resource utilization is incredibly efficient. We only used 1,240 lookup tables, which is just 6% of the board's total capacity. We used 980 flip-flops, a mere 2%, and just 4 block RAM units. Our processor is remarkably compact, but the numbers I really want to highlight are the performance metrics. First up, the power footprint is sitting at just 0.15 watts. To put that into perspective, that is a fraction of the power used by a single standard LED light bulb. That is astonishingly low. It really goes to show that by keeping the architecture simple and avoiding the massive overhead of modern complex superscalar chips, we can create something perfectly suited for energy-efficient embedded applications or battery-powered devices. And then we have the speed, a max clock frequency of 62.5 megahertz. Now sure, if you're comparing that to your 4 gigahertz desktop computer, it sounds pretty small. But remember our foundational rule here. Every single instruction must complete its entire journey, fetch, decode, execute, memory access, and write back, in just one single clock cycle. Hitting over 60 megahertz under those strict deterministic constraints is a very solid, incredibly reliable result. So, as we wrap up this test drive, let's clearly weigh the final trade-offs. Our single-cycle architecture gives us beautifully simple control logic and deterministic execution time. We know exactly how long a program will take to run, because every instruction takes exactly one cycle, no guessing. The trade-off, of course, is lower frequency scaling, because the clock cycle has to be long enough to accommodate the single slowest instruction. If we wanted higher clock speeds and throughput, we'd have to upgrade to a pipelined architecture, but that would force us to deal with the messy reality of complex hazard management. But you know, that is exactly what makes this explainer so exciting. This highly successful single-cycle implementation isn't the end of the road. It serves as the perfect stepping stone. By building a functional, predictable processor from the ground up, we've set a rock-solid foundation. From here, one could begin exploring exactly those advanced concepts, introducing pipelining to boost speed, mastering hazard management, or expanding the instruction set to handle even more complex software down the line. The tools to literally conjure computing hardware out of thin air are right in front of you. You don't need a factory, you just need an FPGA, Verilog, and a bit of curiosity. So I want to leave you with this provocative final thought. Now that you understand the blueprint, with the power of FPGA and Verilog at your fingertips, what kind of digital brain would you design next? Keep learning, keep building, and I'll catch you in the next explainer.